Morning all. 4, 6, 8, 10. Let's get us up the screen. We can talk. Yes, we're up and running. Dun, 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 dun. How's everyone doing today? Anything on your mind? Oh, I've got a cup of coffee. That's all I care about. Not as big as Sydney's. That's not a cup, Sydney. That's like for plants to go in.
It's my entire French press that fits in here.
Yeah, you fill the whole thing up.
I mean, I use a mason jar most of the time, so
Nice.
it's not much better.
These things right here, hydro flasks, they are a ripoff money-wise, but holy cow, do they keep your coffee warm? Oh my gosh.
I've really wanted to get the big water bottle hydro flask, but they're quite a lot of money for a water bottle.
I know. It's pretty hard to justify, isn't it? Gosh.
But I love drinking water, so I don't know. It's kind of worth it.
Yeah.
I have this one.
Have to let it soak a little bit.
This is
Yeah.
mine.
Look at that guy. Monstrous.
It's got the mountains on it. Pay like $40 for it. Don't care.
So Sydney, there's a brand called Arctic, RTIC. They're the cooler version of that is a knockoff of the, what's that ridiculously expensive one?
Yeti.
Yeti. It's a Yeti knockoff. It's the people that made Yeti. Once the patent ran out, they took off on their own and made their own. And so I have an Arctic cooler, and it's the same design. Like if you looked at it, you'd think it was a Yeti. But when I bought that cooler for like half of what a Yeti was, they also sell the kind of the bottle, the drinking bottle thing, and way cheaper too. Arctic. You might take a look at that.
For sure, I will. Thank you.
Kind of a cheapskate, so. Awesome. Okay, so we are wading in for a day and a half into kind of, handling all these kind of conundrums, like, what do you do in this circumstance? What do you do in that? And so I'm speaking a little cryptically, but we are starting off today talking about something called the product rule. And just to kind of build up to that a little bit, if you're sitting here with f of x equals, like, let's just keep it simple, like 5x cubed, you know how to take that, the derivative of that, and it's almost kind of like you're thinking of the 5 as kind of out there on its own. And so you say, what's the derivative of x cubed? And so you say, cool, the 5 is just out there, and then the derivative of x cubed is actually 3x squared. And so the 5 just kind of comes along for the ride. It's just kind of sitting out there in front. It's like, what's the derivative of 5? It's like it just sits there. It's just kind of there. And so then, then you go ahead and multiply the 3 times the 5. And so, this is what we saw happening. In other words, we just said, hey, the 3 gets multiplied by the 5 and it turns into 15. The 5 just kind of comes along for the ride. And so in a sense, we don't care if there's a constant out in front. That isn't weird. It doesn't behave strangely. We kind of just get to kind of sit it there. And then also the other thing that I guess I just don't want to have blown by you, but if I said something like, let's pick a different letter. if I said something like, g of x equals x to the fourth minus 7x squared, the fact that there's a subtraction problem here, like we also say, great, in a sense, derivatives like subtraction and addition signs, we just kind of get to do it separately. G prime, we just kind of get to do those separately. We don't really care that they're subtracted. And so we just say, great, the derivative of x to the fourth is 4x to the third. And then we just throw a minus sign in there. And we don't have to care. Like we don't even have to look at the 7x squared. I'm done with derivative of x to the fourth. The power rule says it's 4x cubed. Then there's a minus sign. And so, okay, now what about 7x squared? Oh, okay, that's 14x. And so derivatives like minus signs and plus signs, constants being multiplied, no problem. But today we're talking about the product, which of course is code for multiplication. And as it turns out, sort of this doesn't work. In other words, what if you had an equation where it wasn't multiplied by a constant and it wasn't subtracted, but it was actually multiplied? In other words, what if you had something like x to the third times, I'll just keep it simple, x squared, those two multiplied. And so you might say, and of course, in this case, you can actually multiply them together. And I kind of did that on purpose, and we'll talk about why in a little bit. Actually, let's make it a little more interesting and say, let's say the second one was like the square root of x. And so you can still multiply those together, right? But now you kind of don't want to. So in a sense, the question might be, cool, does it remain that simple? And I'll throw a question mark over this. In other words, you might say, I know the derivative of x cubed, it's 3x squared. And little side note to myself, since the square root of x is equal to x to the 1/2, we saw that the power rule was fine with negative and even fractional exponents. And so let's see, the 1/2 comes down front. And then I take 1 away from a half. Half minus 1 is negative 1/2. So do you understand kind of why I threw the question mark there? In other words, does that work? Do derivatives ignore multiplication signs too? Can I just do those two problems separately? And of course, the hope would be, I hope so, because that's nice and simple, right? But of course, we can actually answer this question since in this case, you actually can multiply those together. In other words, x cubed times x to the 1/2, since we add exponents in that situation, then that'd be x to the 3.5 or x to the 7/2. Notice I wouldn't want to write it as 3.5. Let's see, or would I? I guess it wouldn't really matter. I'm going to write it as x to the 7/2. So that means y, or h prime of x, is definitely 7/2 x, 7/2 minus 1. Let's see, 7/2 minus 2/2 would be 5/2, right? So like check, like this is definitely true, right? Since I can take the multiplication sign away, like I can actually multiply them, so there is no multiplication sign. And so now I look back up here and say, is that the same answer? If it is, then I could say, sweet, then I can just ignore the multiplication sign. But notice it kind of isn't. In other words, what does this really turn into? Well, 3 times 1/2 is 3 times 1/2, and x to the second times x to the negative 1/2, you have to add exponents. So that'd be 4/2 minus 2/2, which would be 3/2. So are you having that kind of wah, 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 like it isn't going to work apparently because it didn't give us the right answer? Like this is definitely right. And up here, when we said, hey, maybe I can just find their derivatives separately and then multiply them together, like that doesn't work. Does that make sense? So hence this chapter is called the product rule, because when two things are multiplied, unfortunately, you can't just do them separately. And again, it's very important you sort of look back at that green example. we were able to do those separately. Like we can sort of ignore minus signs and plus signs and just do them independently and throw the minus and plus sign between them. And we sort of didn't maybe even notice we were doing that, but we can't ignore. We cannot ignore, my friends. Can't ignore multiplication signs. And maybe you understand division is going to be the same problem because multiply and divide are kind of the same operation. Multiplying by 2 is like dividing by a half, and multiplying by a half is like dividing by 2. So multiply and divide are kind of the same thing. So that's not good. So the question is, how are we going to survive it? Well, notice in this case, we didn't have to worry about surviving it because we were able just to multiply it together and get rid of the multiplication sign, which is probably the way to do this problem. And you may remember when you first learned the power rule, sort of like back in section 3.3, like you had some problem that looked like this, where f of x is equal to, and maybe you had x cubed plus, I don't know, 5x squared on top, and then you had like the square root of x on the bottom. So notice, division. From today's discussion, you might understand that that's not going to be that easy to take the derivative of that mess. But back in 3.3, we were able to, well, actually, kind of like I just did, we were able to actually do the division. In other words, you can get rid of the division sign. In 3.3, we said, hey, I know what x cubed divided by x to the 1/2 is because you're subtracting exponents. That'd be 6 halves minus 1/2, which would be 5 halves. And so I can rewrite this as x to the 5 halves, and then 2, which is 4 halves minus 1/2. This would be plus 5x to the 3 halves. And so now, hey, look, there's no more division signs. Like I don't have to care that they're divided, and it's just the plus sign. And so I can do these two separately. But so now it's easy to find, again, our code for the slope equation, or slope recipe, or whatever you want to call it, is f prime of x. Now it's easy to find that. But if we were not able to do this division, it would be hard. You understand that concept? So today then in 3.4, like we might have some question that says, what's the derivative of f if f of x is equal to x squared, but let's say it's times e to the x? Does that make sense? You can't multiply those together. Like that multiplication sign isn't going away. And so what we learned today is it's definitely not equal to, well, the derivative of x squared is 2x. And then I see a multiplication sign and the derivative of e to the x is e to the x. It's like, that doesn't work apparently from today. Does that make sense? And so, what do we do? I mean, there are things that are multiplied together. I can't ask you this question yet, but later we'll have things like g of x equals x times the sine of x. Like you're not going to put those together. Now you don't know how to find the derivative of sine of x yet. We got to talk about that, in a few days. What's the derivative of trig expressions? How do you find the slope of a trig equation and so forth? I can't ask that today. You can't see that in your assignment tonight. The only things you know are power equations like x to the third or x to the 9/2, and e to the x. Like that's, so this is a question that's going to be in section 3.4. But the point is there's all kinds of crazy functions. Like I could say, what's the derivative of x times the natural log of x? And you'd say, I don't know what to do with that. I don't know what the derivative of natural log of x is. Yeah, you don't. We'll talk about that later on. But the point is there are things multiplied that you can't fix. You're stuck with the multiplication sign. You feeling it? You got it? Like, oh, multiplication sucks. We got to think about this. And from the perspective of, people that, I don't know, if you will, invented calculus, or we're just kind of thinking, how do you, if taking the derivative allows you to find the slope, and that's just cool to be able to do, or maybe sometimes even practical, then it kind of, now what? In a sense, like there are things that are multiplied. So how are we going to handle that? There are things that are divided. How are we going to handle that? Logarithms exist. How are we going to handle those? And so, like, is there a way to handle all these? And for the people that made this stuff up, does it make sense the answer to that is not automatically yes. Well, of course there's going to be a way. Well, there might not. Like maybe there's some equations you can't take the derivative of. Maybe it's impossible. Maybe it is possible, but no one's been smart enough to figure it out. Can you feel that must have happened back in the 1600s, and all they did back then instead of sending text to each other was write some letter? But it's like, yeah, dude, I figured it out. And you know, the couple of nerds thinking about it got all excited. Oh man, I found the derivative of sine. Isn't that exciting? In a sense, that's the road we're going to be walking down. But again, one of the things I hate about the way education works is we're going to march down it because it's like a tour that hundreds of thousands of people have went down. But you know, it's kind of just exciting to think that at some point people asked questions and they weren't sure if there was an answer. And you should be feeling some of that with that project I gave you yesterday. It seems like there's only one line from this sun that would be tangent to this mountain. And so it just feels like, man, there should be some way to find it. But you're lucky because, you know, somebody that likes you asked you that question. Like, I know whether there's an answer or not, and I know whether it's within your ability to level to do. But true mathematics is when people ask questions and they just don't know how, you know, can you find an answer to this? Or maybe it can be found, but not by me. I'm not smart enough. So we are traveling paths that people have walked before, which is just kind of interesting. I'm going to give you an explanation now for the product rule. I'm going to make it for you. The rule about handling things that are products, the product rule. I'm going to give you an explanation from a book I found. How did I find this book? But I think it's called Calculus Made Easy. Maybe I'll share a page with you on this later on, but I really like it. It was written in the 1800s by a guy that I don't know, explained calculus. It's kind of like the original version of Calculus for Dummies. I mean, most of us think more simply. And what I want to do is build this rule for you as opposed to just tell you what it is and then prove it. I never liked that as a student. Like, you're telling me the rule, like you don't need to prove it. You're probably not lying to me. But the question is, like, how would you figure out what it is? Like, how would you build it? How would you make it? And I'm sort of indebted to this guy. I've sort of forgotten his name all of a sudden. I didn't prepare. Actually, it's in my notebook. I guess I'll look really quick. Sylvanus P. Thompson, Calculus Made Easy. I'm indebted to him for what I consider to be a way better way to explain this than, I don't know, I've seen any other place. And as I said, his approach is just to explain things really simply. And some of the way I teach this class is based on my thinking from him. But let's look at it this way. So I love to use the word consider. Consider the equation y equals, notice I'm not saying f of x, y equals, and then I'm going to say u times v. But you got to understand that, you know, u is kind of like x squared. In other words, u is some function made of x's. What I don't want to write is u as a function of x. It's messy. I just want to say u, and you just have to think of that as, well, like what we did up here. In other words, f of x is equal to junk times junk. So the u is the x squared, and the v, we'll say, is kind of like the e to the x. So do you see what I mean when I say u times v? It's like, that's not the letter u, that's not the letter v. That just stands for two different functions that are multiplied, and I can't multiply them together to make one because they're totally different. Like, I can't multiply x squared times e to the x, or you can't multiply x times the sine of x. You can't put them together. Like, you're stuck with the multiplication. And so here's the concept. Like, what does it mean? What does it actually mean to take a derivative? Well, do you agree that what we tried to do a while ago was, we said, okay, cool, you're here, right? And then we said, what would happen if you just, well, changed it a little bit? In other words, the x got a little bigger and the y got a little bigger. Does that make sense? So if this is the point x, y down here that I started with, then this point up here is x plus a, let's see, how am I going to say this? I think I'll say it as a tiny bit of x, dx, a little bit of x. That's what dx means, is a tiny amount of x. I could say delta x for change of x. It's the same thing as h. In other words, x plus h. H is a tiny amount. But the reason I'm saying it this way is just because it's a little tiny bit of x. I'm adding a little bit to the x, and then the y I'm getting by adding a tiny amount to the y. And so basically what that does is just say I found a second point, but it's really close to the first point. Like this is what we've been doing with calculus. And so that's what change is, right? You're saying, hey, there you are at xy, and now a tiny amount of time goes by and now it's changed a little bit, right? 2 seconds has passed, the tree is 4 feet taller. Or 1 second has passed and the tree is 1 millimeter taller. Like they're independent of each other because one is time and one is the height of the tree or something like that. But this is what a derivative is change. It's a tiny amount of time passes and a tiny amount of change happens in the volume or the speed or whatever the case may be. Okay, cool. So then what does it mean to kind of take a derivative of that expression? Well, you would say something like, then y gets a little bigger. So I'm taking this y up here and saying, okay, y just changed, y got a little bigger. And then u got a little bigger and v got a little bigger. Isn't that like, that's what change means, right? All of them got a little bigger. Everybody got a little bigger. But these two things are multiplied, right? So I kind of need those parentheses, because what does it mean to multiply those two things together? Well, because of those plus signs and because of the distributive law, multiplying that together is not so nice anymore, right? Like that's kind of messy. And so, okay, let's multiply it out. So I say, fine, I don't know what to do on that side, but here I can go u times v, and then u times dv, and then du times v, and then du times dv. And again, you should be thinking, what is this? Where is this going? Like, what sense is this making? But let's start cleaning this up and thinking about what we have sitting here just a little bit. So remember, this was true. It was true that y was equal to uv, correct? So let's use that fact. Does it make sense that I could replace this with y then, since y is equal to uv anyway? And then if there's a y on both sides, like couldn't I subtract y from this side and subtract y from that side? So now I have dy equals u dv plus v du plus du times dv. Like that was actually a little simpler. So it's just basic algebra. Again, you're not going to find this in your math book, like this way of explaining it. I like this way of explaining it myself. Now, what does this mean? That's a tiny amount of a tiny amount of something. Does that make sense? So it's like I go out of my yard and I'm going to take one blade of grass out of the yard, a tiny amount of my yard. So I pull one piece of grass, but then I say, now I'm going to take a tiny amount of that piece of grass. What do you got now? How much of the lawn do you have if you follow that set of directions? What's a tiny amount of a tiny amount of something? Well, it's like next to nothing. Does that make sense? In other words, this is on its way to zero. That's kind of what I'm getting at. If du is a tiny amount of something and dv is a tiny amount of something, and then you multiply those two things together, now you got virtually nothing. So keep in mind, aren't these on their way to 0 too? Remember we let h, or how much bigger the second point got, we let it go to 0. And remember, we always said we want to do that, but we just can't do it too soon. In other words, if I take my statement right here and say, oh, okay, let's let all these tiny amounts go to nothing. Well, then notice the whole thing still says 0 equals 0. So it's like in a sense, we can't do that just yet. But at least with that du dv, I have, 0.00001 for one of them, and then 0.000003 for the other one. And if I multiply those, you pretty much got nothing. I mean, does that make sense? So dy, du, dv are tiny, but du times dv is really tiny. I mean, that's the idea here. Again, I'm just trying to give you a conceptual understanding of where this is going. And we're almost done. Now I'm going to do something algebraic again. I'm going to divide both sides by dx. So if I do that, then I have dy dx equals u times dv dx, or dv divided by dx, plus v times du divided by dx. So all I've really done is two algebraically simple steps. I substituted uv for y, and then it allowed me to subtract both sides out. I noticed that du dv would be particularly tiny. And then I just did another simple algebra move, which is divide both sides by dx. We're done. That's actually the product rule. But let me help you understand like what this is saying a little bit. So what is like dy dx? What does that mean? Like, what is that? I don't even know what you're talking about. Like we have a symbol for derivative, and that's like f and f prime, right? Well, if you had an equation like y equals 4x squared plus 3x or something like that, when we say y prime, aren't we effectively looking at the other side and we're taking the derivative of the other side, well, with respect to x? In other words, we look at that 4x squared and we say, okay, the derivative of 4x squared with respect to x, or, because it's made of x's, is 8x, and the derivative of 3x is 3. My point is dy dx is another way to say derivative. In other words, you're seeing how y changes based on how x changes. That's what you're doing. That's just another way to say what a derivative is. It's another way to think about what a derivative is. So the symbol y prime by itself kind of doesn't mean anything. We just say, oh yeah, that little dot, that means do the power rule. But dy dx is actually much more informative, because it basically says if you change y a little bit, then how will that change x? Or if you change x a little bit, how will that change y? And so, as a practical example, I might look at my tomatoes and go, wow, those things aren't growing at all. I think I'll change how much I'm fertilizing it. I'll slightly change how much I'm fertilizing it. I'll put a little bit more fertilizer on it. And then I stand back to see how the tomatoes grow different. Does that make sense? I change one thing and I make a tiny change in one thing and I see how it changes something else. And so when you say dy dx, that's actually a little more informative than just saying y prime, because you're saying, hey, I want to change one thing and I want to see how it causes the other thing to change. So the point is really this is just y prime or f prime of x. I mean, those are kind of all synonymous ways to say derivative. So to write the product rule then in its simplest form possible, product rule, I think the coolest way to say it is basically this. If you say y equals u times v, and understanding that those are functions of x, then y prime, well, look at the directions up there. Y prime, what is it? It's u times v prime. If I'm looking back here, doesn't that say leave the first function alone, u, but then multiply it by the derivative of the other function. In other words, leave u alone, but then multiply it by the derivative of the other function. And then plus, what does the second one say up here? It says leave v alone times the derivative of u. And just to make it a little more memorable, I'm going to kind of turn the order around. Like this is effectively what the product rule says. So it's like a little more complicated. So if you have two functions that are multiplied together, you got to like do more stuff to it, right?
Is that supposed to be uv prime plus uv prime?
No, it is not. Sorry, it's hard enough to understand if I can't even explain it. That second one was du dx, and so that's u prime. Sorry. So just to go back up here, since I managed to screw this up, does it make sense? That's v prime. dv dx means just take the derivative of whatever that equation is, take its derivative, and this says, you know, take the derivative of u. So it's u v prime times u prime or plus u prime v. In other words, take the derivative of one times the other left alone, plus take the derivative of the other times the first one left alone. And that's a rather remarkable, remarkable way to come up with that. So again, I'm giving you a shot at having a little intuition as to where this come from. I could have just told you that. I could have said, here's the product rule. Anybody want me to prove it? Raise your hand if you want me to prove it. And most people are like, I don't need proof, or I don't really care. I just want to kind of know how to do it. But we made this, and so you're going to want to go back and, you know, look at my notes a little bit. But first of all, let's just like try it out and let's see that it actually works. So back here, we took this problem. And we did what we thought would make sense, which is just to take those two derivatives separately. And it didn't work, right? And in that case, we were able to actually multiply the two expressions together. And so we sort of knew what the right answer should be. We definitely know the answer to this is supposed to be 7/2 x to the 5/2. But what I'm saying is, let's go back now and take a look at this original problem and use the product rule and see if we can also get 7/2 times x to the 5/2 if this rule actually works. So, you know, what does this rule mean? And then see if we can actually get it to work. So x cubed times the square root of x. So let's revisit f of x or y, whatever, equals x cubed times square root of x. And we just decide, I don't want to multiply them out. I think I'll just use the product rule. As we said, in this case, you could actually multiply them and get rid of the product. Generally speaking, if you can get rid of the product, then good, because the product rule is a little more complicated. But what if we decide not to? Well, in a sense, this is our u, and this is our v. So what do these directions say? It says to find f prime of x or y prime or dy dx for that matter. Like all of those are just ways of saying the same thing, which I find a little annoying. From your perspective, I'm just learning this, and it's like, let's not learn 3 ways to say this. How about just one, and you can show me the other 2 later. That's annoying. But you might see that in your assignment. My open math, for instance, was all the problems are written by numerous different teachers that just contribute the problems. And so, in a sense, these 3 ways of saying, go find a slope equation, it can be like one person's favorite is dy dx because it speaks a little more clearly as to what you're doing. Another person's like, that's too cumbersome. I'm going to write y prime. And so you might see more than one. So this set of directions says you leave u alone. Okay, x cubed, I left it alone. Times v prime. And remember we said v then, that's the same thing as x to the 1/2. So times the derivative of x to the 1/2. Well, power rule says 1/2 comes down front. I subtract 1 from that 1/2 and I get negative 1/2. Okay, cool. then there's a plus sign. Okay, product rule is always a plus sign. That's kind of interesting. Could have been a minus sign. It's always a plus sign. And then I take the derivative of u. Since that's the first one, that'd be 3x squared. There's the derivative of u prime, and then times v left alone, or the second one just left alone. And again, I'll write it as x to the 1/2. So do you see that that's what the product rule is saying? So let's see, let's clean this mess up. So x to the third times x to the negative 1/2. Again, I add exponents. Since 3 is 6/2, then I go 6/2, well, minus a half, that'd be 5/2. And so this is now x to the 5/2. And then 1/2 is the only constant that just kind of comes along for the ride. It's multiplied. And then plus sign. And then same thing. Let's see, x to the 2 times x to the 1/2. Well, 2 is 4/2, and now I can add those exponents because they have a common denominator. 4/2 plus 1/2 is 5/2. So I have x to the 5/2, and then the 3 comes along for the ride. And so now I notice, hey, that's interesting. Look, I have a half of this thing plus 3 of those things. So it's like a half times g plus 3 times g. Oh, I just add them together. So wouldn't that be 3.5 x to the 5/2, or 7/2 x to the 5/2? Hey, that worked. That was the answer we were supposed to get, wasn't it? How do you decide when you're looking at two of these things multiplied together? How do you decide which one is u and which one is v? Is it like x cubed is u and the square root is v? Or is it like, no, this is the v and this is the u? Like, how do you decide which one is which?
It shouldn't matter too much, should it?
That's right. It doesn't make any difference, because down here in the end, weren't we adding them together anyway? So it actually doesn't make any difference. So if you don't, for some reason you don't like it, then turn them around or whatever. I like to think of it just so I don't screw it up, because we have a number of other rules to learn in this class. I like to think of it as just alphabetical order. U is the first one, V is the second one. I usually don't care. Like, I just take them in order. The first one's U, the second one's V every time. But if you want to rewrite it, or just label it weird like I just did a second ago, knock yourself out. It doesn't make any difference. And because you're adding them, right? Isn't 3 plus 2 the same as 2 plus 3? Like, who cares which one is which? Addition does not care what order you do it in. Now, if it's subtraction, then it would matter, right? If it's subtraction, it would matter. 5 minus 2 is not the same as 2 minus 5. But since it's addition, it doesn't care. Multiplication doesn't care. 5 times 2 is 10. 2 times 5 is 10. That's what commutative and associative properties of algebra say. Maybe somebody bored you with that before, but that's something you got to have the feel of. So this problem, because it's multiplication and addition, doesn't even matter what order you do any of this stuff in. You're going to get it right. That's kind of the idea. Sydney.
So earlier you said there was a significance with using y instead of f of x. Is that because you find like two functions within this equation to find a derivative and then add them together? Is that why it's significant?
No, I'd say the advantage of using y is just that you realize it's a y coordinate. In other words, when you put in an x of, say, 3 into the equation and out pops a 7, you go, oh, that's a y. And now I can graph the point. So, I like y for that reason, because then it's like, yeah, I totally get what this is. But when you put f of x there, that's kind of cool, because now you have a symboled way to say things. In other words, it's kind of like, well, I change the fertilizer, and now what comes out of that is how much does it grow. So it's two ways of saying the same thing. So no, I'd say it doesn't make any difference.
Okay, cool.
Let's see. So, well, let's go back and now let's try. And I'll start. I don't know. Let's Because in the book, it's not always F. It's, you know, sometimes it's just some other random letter. But what if it was X squared times e to the X? Like, what do you tell me? Like, what do you think the derivative of that is? Based on the most holy product rule. So let's say you're taking a test, or more likely it's like 6 months from now and you've totally forgot all this stuff. Like this is an easy rule to use for today's assignment because it's the only kind of questions you're going to get, right? But 6 months from now, you're going to know like 6 rules and you're going to have forgotten all this stuff, and it can all jumble together. And so, you know, you're kind of wondering like, do I still remember how to do this? If you ever need it. So go one step further and find G prime of, I don't know, -2. Let's just check our work. Like rather than me just, I'll do it in a second, but rather than me just doing it, why don't you just check your work? So G prime of -2. So this time I'm going to use the graphing calculator. Again, I like Desmos better, but let's use the graphing calculator. I found a computer version of something just went wrong. Let's see here. Share screen, share that screen. So I found a computer version of the graphing calculator. So now I don't have to point that stupid camera at it. Uh-oh, is this working? Hey, it is working. So I wonder if you can understand how I'm going to check my work here. Like, how am I going to use this to check my work? So you definitely have an answer now. You definitely think you know the slope of this curve. Don't forget what you're doing here. We're always finding slope. It's all we're finding. What are we really doing? We're finding the slope of this curve at -2, at x is -2. So I'm going to go in and type in our equation. If I say x squared times, where the heck is e? I think it's that little blue guy right there. E raised to the x, right? And I'm going to say zoom 6. So there's our graph. And notice that's really ugly. Like that's a really ugly graph. So I hate graphing calculator. Desmos is a way better graph. And then also I can see, and you should be able to do this, but notice the action in the graph is kind of like right here, but it's all jumpy and looking stupid. So I'm going to change the window. In other words, I'm looking at this and saying like, what would make a better window right here? And there's all kinds of ways to do this, but I'm going to use one of the cheap versions. I'm going to use Zoom Box. Zoom Box, you click like the upper left-hand corner. Is this right? I can't remember. Looks like I can't remember how to do this. Zoom Box. Not so used to. Oh, I think I actually have to hit the cursor. That's what I have to do. So I'm going to take the cursor over to here. I'm thinking of this as the upper left-hand corner. Like that's the upper left-hand corner. Say enter. And now I'm going to take the cursor over to the right-hand corner. I think this is actually more time-consuming than just typing it. In other words, what I'm really thinking is, how about if I make the the y max 2 and the y minimum -1. It'd be better just to type that in. And then the x minimum is like -4 and the x max is like 1.5. So now I'm going to get a better look at what this graph looks like. So notice it goes up, 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 and then it kind of turns down, 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 turns around, kind of bottoms out at 0, and then it takes off again. And so at least I can see it a little better. And now I'm going to help you check your work. So now if I go back in here, and I showed you this button already, second calculate. And I go down to, well, remember that symbol, dy dx. This is we've seen this before. It says change of y over change of x. Notice that's the symbol that whoever the nerds that made your calculator word chose to use. So I say that's the one I want. I think I got to hit 6 to do that. And then it's sitting here waiting for me to say what point am I interested in. And so we said we're interested in the point -2. And so my question is, did you get that for a slope? What'd you get for a slope? This is not what you got. What'd you get?
I got 0.
You got 0. Notice, can you see that that's, remember I told you the calculator is not doing calculus. It's finding the slope by getting 2 points really close together. Do you see the answer it gave as scientific notation for a number that's ridiculously close to 0? Because this is going to happen from time to time. So that's really moved the decimal point 8 places to the left. So that's actually the number -0.00000004. Oh yeah, that's pretty close to 0. So if you got 0, then maybe you took the derivative right. What about -1? Let's go check -1. If I go second calculate and I say I'm very interested in what the slope is at -1. Notice it's predictably negative. Now in your case, you should be able to give an exact answer to this, leaving E in it. And that's the kind of thing my open math might want, right? If it was asking for it, because none of us look at that decimal and recognize it, right? In my case, I'm just looking at a decimal. I don't recognize it. I'm not surprised it's negative. I'm not surprised it's small, just from looking at the graph. It's a small negative number. It's around a third, -1/3, but you could give an answer that's a little more accurate than that, leaving E in it, if you will. So that should make sense to you. So again, don't forget, this is just how do you find the slope for any curve? And now we're starting to get some complicated ones. X² times e to the x is probably a curve you've never looked at before. And it'd be really exciting if that modeled how something grew, but mathematicians just say, who cares? It's just cool that it's there. Goodbye, calculator. While I am here, while I'm over here, if I quickly go into my open math, and maybe you already found this before, but if I go into my open math in course information, see that it says Calc 251 notes and basic trig identities. I'm going to open this up because you need to print this. Find a way to print this, even if you're not old school like me and still have a printer. Because you kind of want to have this available. For the most part, you'll be sitting by your computer and you can just pull it up. But notice this is a 1-page doc. And this is what you're going to have when you take every test. And notice you now understand the first part of this. Like this is all the cheat sheet shortcuts that I'm going to teach you in this class. And so these two definitions for a derivative, how to find a slope. The power rule. If y was equal to x to the n, then y prime would be n times x to the n minus 1. That's just a reminder to you when this all gets jumbled up on a test. You now know the product rule, which says if y equals junk times junk, then y prime would be u prime v plus uv prime. Notice that's written in a different order than what I wrote. I think it's written in a different order than what I wrote on my paper. I can't remember. And notice I even reminded you that u and v are both functions of x. So there's a reminder of the product rule. Notice we have the quotient rule, the chain rule. How do trig functions work? What's the derivative of natural log? What's the derivative of log? What's the derivative of exponential? What's the derivative of inverse trig? Like this is what mathematicians do is they say, oh, derivatives are cool. Let's go take the derivative of everything. So we're going to march our way down this, but you have access to it right now. So that's cool. not hard, is it? It's just not hard. Baby, come back. All right, we're back in the building. So then you would say the derivative of x squared is 2x times the second equation left alone, plus the first equation left alone times the derivative of the second. And of course, e to the x is a weird one because, as you are learning, the derivative of e to the x is e to the x. And so, again, in a sense, you could say, I am now done. There's the answer. But you could also clean this up a little bit. And so, you know, different, as I say, for my tests, I don't care when you stop, but you could look at this and say, hey, look, they both have a e to the x in them. I'll take e to the x out, and that would leave 2x plus x squared, or maybe you like writing them in order, x squared plus 2x. Like, that's a nice answer to this, if you will. And so if somebody wanted an exact answer, God forbid, for -1, you'd say, oh, okay, that's e to the -1 then. And that's -1 squared, and that's 2 times -1. And so what is that what happens as a result of that? Well, this is +1 and this is -2. So that becomes -1 inside there. So I have -1, and then maybe you recognize that e to the -1 is a little weird looking. So you put it on the bottom. Like, that's the nicest looking answer you could give. And so, as I said before, it's like none of you looked at my calculator answer a second ago and went, oh yeah, -0.367, isn't that 1 over e? But you know, if I bust out my calculator now and I type -1 divided by e, it says, and this is a really important thing, I think, in my opinion. So here's the exact answer. And then, you know, tell people I am now rounding this off, and then you round it however the heck you want to. I'm lazy, so I'm going to stop right there. That's awesome to be able to do both, I guess, is what I'm saying. In the real world, nobody cares about the exact answer. It doesn't really do anybody any good. They only care about the approximate, but it's kind of cool to have it as accurate as you want. You should be able to give both of those answers. And the point is, you can check this. That's the key. I can check it. I can go to technology, Desmos or graphing calculator, and kind of make sure that I didn't screw this up. So it's working. The product rule is working. I mean, that's the idea here. Now, the other reason I just showed you that note sheet is, notice there's all kinds of cool product problems I could make up where we have two distinct functions times each other. Like, what's the derivative of sine times tangent? Or what's the derivative of cosine times natural logarithm? But we don't know what the derivative of cosine is yet. We don't know what the derivative of natural logarithm is yet. There is not very many derivatives that we can actually take right now. There's the only two things I can multiply together are like x cubes, x to the fourths. In other words, what mathematicians call power equations, an x to a power. And then I can get e to the x in there, but that's like the only two things I can multiply right now. There's not a lot of problems I can do just yet with this skill that I have called the product rule. But let me show you one thing that's kind of cool here, because this, I have a fear that this comes up in your assignment, but let's just try this out. Like, what about e to the 2x? Like, would the derivative of that, again, I asked the question mark, would that just be e to the 2x? In other words, we said the derivative of e to the x was e to the x, so would e to the 2x be e to the 2x? So again, as a math teacher, I could just say yes, or I could say no, and then it'd be like something else for you to memorize. But what I'm trying to do in this class is teach you how to think, in this sense that if you know your stuff algebraically, you could actually answer this question yourself. But it would have to occur to you that e to the 2x could be written as e to the x times e to the x. Would you agree with that? In other words, I rewrote it as two things multiplied together. Well, now because I rewrote it as two things together, and you know for sure what the derivative of e to the x is, why don't you, real quick on scratch paper, use the product rule to find the derivative of e to the x times e to the x, and then you'll be able to answer my question here. Like, you know, how does that work? What if it's not just e to the x? What if there's a number there? What if it's e to the 4x or e to the negative 3x? Or what if there's a number there? Like, you know, what happens in that situation? I'll give you a second. You can answer this yourself. You don't need people to tell you. I hope that you can now say yes or no to what I have circled in blue. You answered it yourself. Oh, apparently that is true. Oh, apparently that's not true. You should have an answer to that. And I didn't have to teach you anything new for you to answer that question yourself. You just had to have a little creativity. Well, if I think of e to the 2x as two things multiplied together, then I can say the product rule says the derivative of the first times the second one left alone plus the first one left alone times the derivative of the second. And of course, again, the derivative of the x being e to the x makes that really weird looking. So let's see, well, isn't this e to the x times e to the x? I add x plus x, which is 2x. And the same thing happens over here. And if I have one of those plus another one of those, don't I have two of them? So apparently the answer to that is no. The derivative of e to the x is e to the x, but the derivative of e to the 2x is not e to the 2x. It's 2e to the 2x. Now, we won't continue that discussion, but I don't know about you, but you should have other questions in your mind now, like, well, what's e to the 3x going to be? Or what about e to the negative 1x? Or, you know, because in this case, because it was e to the 2x, I was able to write it as junk times junk. But if it was e to the 3x, that's junk times junk times junk. Or if it's e to the negative 1x, now, like, how do I write that as a multiplication problem? I mean, we could go down that road. We're not going to, but I just want to encourage you to kind of think about this. If that happens to come up in your assignment, in other words, if they say, what's the derivative of x cubed times e to the 2x, you do need to know that derivative of e to the 2x is not e to the 2x. I can't remember if that comes up in your assignment or not.
So Doug, for the product rule that we're doing now, if you have to do 3 products, do you multiply like u times the derivative of v times the derivative of c, the third product?
Yeah, that's a wonderful question. One of the things you could do to avoid that problem, and we'll get to this later on, if it was something like, just to make it a problem that we could actually survive. If you had this, again, what you should say is, I'm just going to multiply those out and get x to the 9th. Does it make sense that if that's x to the 9th, then y prime is clearly 9x to the 8th, right? That's the right answer. Like, don't make a product rule problem out of that, because you're going to suffer. But Connor's question is, like, you know, could I survive this some other way? So I'm not going to completely answer your question, but if you thought of y as being x squared times x cubed times x to the 4th, in other words, by grouping it together, you just sort of collectively called this u and this v, you could answer that question yourself. But when it came to take the derivative of u, in other words, when you need the derivative of that first expression, does it make sense that's like another product rule inside of it?
Okay, I see. Yeah.
Now, is there a shortcut to all of that? Like, is there some way to like write out a giant product rule where, and this is what you were hypothesizing, and so I compliment you for thinking like that, Connor, because you're, you know, automatically answering, you know, how would I handle this situation? It isn't always just two things multiplied together. You know, is there some kind of cool way to write that out where it's like, you know, this is u and this is v and this is w, and there's like a product rule for 3 of them, Keep in mind, there could be a problem that's like, what's x times e to the x times the sine of x? Like you're stuck with all three of them there. So, I'm going to have to do a product rule with three different things. You won't have to do that in your assignment today. I mean, I can't really give problems like that right now. And of course, it's only mathematicians that make up crazy stuff like that. But we need to know what the derivative of sine is before we can even think about that. So we'll think about product rule more later on, and it will come up a lot as time goes on. So we will answer that question. So that's a really good one. Let's see, we have 20 minutes. Let's switch gears then and look at the second of today's two rules. This was also on the note sheet, but I didn't stop and note it. But the quotient rule, in other words, what happens, of course, quotient is math speak for division. Like what if you have two functions that are divided by each other? What do you do then? And we already saw that multiplying is sort of a lot more complicated than you would have thought. And division is almost horrifying. So let's see if we can survive that. So as an example, if I said, let's do kind of one that I did earlier, like x cubed plus 2x squared over the square root of x. As I said, you can do that right now because you can get rid of the quotient. That doesn't have to stay a quotient. So let's do that and first get the right answer to this. So since square root is really 1/2, and now I can sort of work with the exponents, then I can say, okay, well, I can actually keep simplifying that. X cubed over x to the 1/2, because you're subtracting them, that'd be 6/2 minus 1/2, which is 5/2. And so this is x to the 5/2. And then plus x to the 4/2 minus 1/2, that'd be x to the 3/2. Does it make sense that, yeah, the quotient's gone? If you gave me this problem to do now that I know all of calculus, this is what I would do. Like the quotient rule is horrifying. If I can avoid it, I'm avoiding it. You'll see what I mean in a minute. So now I'm actually in a position to find the derivative, and I don't need to deal with like, what's the quotient? Maybe you can already appreciate that y prime is not going to be the derivative of the top 3x squared plus 4x divided by the derivative of the bottom. The derivative of x to the 1/2 would be 1/2 x to the negative 1/2. It's not going to be that. Can you see that that's going to be the case? Like it wasn't that easy for products, right? When two things were multiplied, you couldn't just do them separately. This is not going to work. You can't do, I'll use English here, top and bottom separately. And again, I wish you could. Do you understand that? Like if you go to the graph of whatever this function is, it has a slope. I wish that second equation I made right there, I wish that would work. It's not like mathematicians say, that's too easy. Let's just make the derivative harder than that. It doesn't work. Like the derivative is trying to find the slope of the curve. And if you use that recipe that I just circled, it doesn't give you the slope. And so it's not mathematicians that are making this stuff hard. It's just like that just doesn't work. So you, of course, would say, no, since I was able to simplify this, the derivative of x to the 5/2 is 5/2 times x, and then I got to subtract 1 from 5/2. 5/2 minus 2/2 would be 3/2. And then I multiply 3/2 times 2, which conveniently turns out to be 3. And then 3/2 minus 1. 3/2 minus 2/2 is 2/2 is 1/2. And so this sort of has to be, this has to be it. And that's certainly not the same as that. And so that's why that doesn't work. This is clearly the right answer. And so again, in this case, you're able to avoid the division problem, but you're not always able to avoid it. What if I said, what's the derivative of x divided by the sine of x? Like you can't get rid of the division sign there. And so you're stuck dealing with it. And so how am I going to, what's the recipe? How am I going to get rid of it? Clearly, this is the right answer. The question is there some way to kind of go straight from here to here, leaving the division in it, so to speak? What do I do? And you might even predict it has some combination of what we just saw. Since division and multiplication are related, it's going to be like the derivative of 1 times the other one left alone, the derivative of the other times the other one. Like that might be a part of this somehow. But again, let's see if we can build this. Thanks to Sylvanus P. Thompson. Let's build the quotient rule, considering that y equals not u times v, but u divided by v. What would Sylvanus P. Thompson approach to this be? Well, we don't know because it's division, but let me show you an easy way to get out of this mess. Let's just do some basic algebra. If I multiplied the v over to the other side, then isn't the equation kind of a product rule now? And if we went to take the derivative or, change, like how is it changing? In other words, that's the derivative. Well, the derivative is y gets a little bigger, v gets a little bigger, and u gets a little bigger. Isn't that what ultimately conceptually what a derivative means, is they all get a little bigger? And so now, like last time, I want to multiply all of this out. So I'll have u times v. I'm sorry, that's not true. I'm over here multiplying this out. I have v times y or y times v. I don't know which way to write it right now. I guess I'll write v times y. And then I have y times dv. If I multiply this out. And then I have v times dy. And then I have dy times dv. And the other side, no changes. And as we said before, a little bit of a little bit is kind of on its way to zero. So that's kind of cool. And back here, we said that u was equal to v times y. So that means I could replace this with u, correct? If I wanted to. Why is that cool? Algebraically, why is that kind of neat that I did that?
Because it cancels on the other side.
Exactly. That means I can subtract u from this side and subtract u from that side. So just to rewrite what I have y times dv plus v times dy equals du. And that's kind of like what we had before. Like this is no different than what we had before. But just keep in mind, what I'm really looking for here is I'm trying to find dy dx or y prime. That's what I'm trying to find. So notice there's my dy, if you will. And that's kind of what I want to find. I want to get dy by itself. And so since I'm looking for dy dx, then I'm going to leave that on that side and move the y dv to the other side. So I could say v times dy is left on this side, and then du over on the other side if I subtract y times dv over to that side. And then to finally solve for dy, I'm going to divide both sides by v. So now I have dy equals du minus y dv all over the top of v. And then in order to get what we're after here, which is dy dx, I kind of need dy dx. So then I'm going to do kind of what we did on the other side, which is like divide both sides by dx. So I want you to think about that for a second. Like, what should I do now? Well, when I divide the left side, I'd have dy divided by dx. When I divide the right side, again, how's your algebra skills? What am I really dividing on the right side? Well, du gets divided by dx. Which one of these gets divided by x? Is it y or is it dv or is it both?
It's both.
Because there's not a plus sign between them, it isn't both. In other words, it's really it's y dv, but then divided by dx. Like that's in a sense how you'd write it. But you're not doing it to both separately because there'd have to be a plus sign between them. It's kind of like saying if you have 6 times 7 and you divide by 2, which one of those gets divided by 2? It isn't both of them because that's a plus sign. In other words, the 6 divides by 2 easily because it's an even number. So you'd go, oh, that's 3. And then you'd finish by going 3 times 7, and the answer is 21. 42 divided by 2 is 21. If you take 6 divided by 2 and get 3, and you take 7 and divide by 2 and you get 3.5, you get 9. The answer is not 9, it's 21. So pick one is the idea. So because of the language that's there, I'm going to pick the dv to divide by it. And then does the bottom get divided by it? No, because you're not doing it top and bottom. If you did it top and bottom, you're dividing by 1. Again, there's just a lot of algebra here that you might kind of screw up.
Wouldn't you only do the bottom though, if you were dividing by?
Yeah, and in a sense, that's kind of what's going on. Like, keep in mind, dividing by dx really just means multiplying by 1 over dx. And so I could have just stuck the dx on the bottom and said it's v times dx and left it alone. But I just chose to actually divide it. In other words, it's kind of like there's a dx sitting down here, and I chose to say, oh, that gets divided. And then because of the minus sign, so does this one. That gets divided too. So I just sort of chose to do that. And the reason I did that is because I want this to, like right now, it just looks like a big mess. It isn't very memorable. I can't really even tell what I'm looking at. But I'm just saying this is kind of cool now because I can call that u prime, which is a nicer, cleaner way to write it, right? And I can call this v prime. That's why I chose to divide by what I wanted to divide by. It's about to get better. And again, I'm not asking you to make this on a test. I could. I'm just asking you to use it. It's already sitting in the note sheet. It's this, a little bit hard to memorize, but if you're curious, this is how to build it. Now, I still feel a little bit stuck, but go back to where we started. Remember that y was equal to u times v. So that means I could replace this with, I just said u times, but I wasn't even reading correctly. It's u divided by v. Y is u divided by v. So and the reason I'm replacing that is on the other side, there's no y's over there. Does it make sense? There's just 2 equations, u's and v's. There's sine of x and x or something like that. I don't really want that y over there. So this could be called y prime. So what do I have now? I have y prime equals u prime minus u over v times v prime divided by v. Again, true, but it's very confusing to look at. I don't like fractions over the top of fractions. So you people that are good at algebra, what should I do to the top and the bottom of that so I don't have fractions over fractions? Just to clean it up.
Multiply by v, right?
Multiply by v. Because that says on the top, u divided by v. The opposite of divide is multiply. So if I said, I think I'll multiply the top by v, that's fine as long as you do it to the bottom. Notice I have a choice algebraic. I can multiply both sides of the equation by v, but I don't want that y screwed up on the other side. So I want to multiply the top and the bottom by v, which is multiplying by 1. And then it's just going to change the way it looks. And you know distributive law, thanks to that minus sign, This gets it and this gets it. So what do you have? This is the quotient rule. We're done. Quotient, can't spell, quotient rule. U prime, whoa, slow down. Kill the motor. Quotient rule says that if y equals a function divided by a function, u over v. And notice now it matters, u over v. Is 6 divided by 2 the same as 2 divided by 6? No, like we can't just interchange these. There's a top one, there's a bottom one. What is y prime? Well, it would be, when I multiply v over to this, it'd be u prime times v minus, and what happens here, this v cancels with that v, minus u v prime all over v squared. That's, if a person had to memorize this, that's possible to memorize. Let me rewrite the product rule down here right next to it. If y is u times v, then y prime is u prime v plus u v prime. Stare at, again, if you needed to memorize this, my philosophy is you do not need to memorize this. Get your phone out, say, talk into it. What's the quotient rule? Let's try it real quick. That just sounds like fun. Siri, what's the quotient rule?
Here's what I found.
Hey, found it. Like in the world we live in, you don't need to memorize things. So I've already got it written in your note sheet. You're going to have a note sheet for every test. But if you did have to memorize it, do you see the similarities between these two rules? Notice that these two statements are identical, except for what? I know it's obvious, but somebody put it into words. They're identical, except for what?
It's divided by v squared.
Yes. And what else? One's divided by v squared, one's not.
And it has, the quotient rule has a negative.
Quotient rule has a minus sign. Product rule is a plus sign. Quotient rule is a negative sign. And then you got to divide by v squared. Now that's a, wouldn't you say this is a fairly complex recipe for finding slope? If I was inventing this, it wouldn't be that complicated, but it's like there just isn't another way to do it. I mean, that's what this is saying. It's just hard to believe. So it really is, it's almost the same as product rule, except for there's like an extra v squared. And notice the cool thing is v squared, it isn't per derivative of it, it's just square it. So let's do this quick example and then we'll finish this out. So we'll be done. So we said, we had this problem right here, and we knew that this is supposed to be the answer right there. Do you agree with that? And so let's see if we can get that top one correct before we go, using the quotient rule, just to kind of see if we can actually use the dumb thing. X cubed 2x squared, square root of x. And let's try to use the quotient rule to pull this off. So what does the quotient rule say? Quotient rule says u prime v. So notice this whole thing up here is our u, and that's our v. And this time we can't mix them up because you do very different things to them, right? So the quotient rule says u prime. Well, I know what u prime is. U prime is the derivative of x cubed is 3x squared. The derivative of 2x squared is 4x. So there's the u prime. And then v is left alone. So all of that is multiplied by v, which is just, I think I'll, in the interest of time, write this as x to the 1/2 power because I will be able to clean that mess up, right? And then it's always minus. And then it's u left alone, which is x cubed plus 2x squared. So there's the u left alone times v prime. which is 1/2 x to the negative 1/2. There's v prime, all divided by what?
V squared.
Yeah, whatever's on the bottom squared. Now notice in our case, what's on the bottom is the square root of x. So it's actually just going to be x, but I'll go ahead and write the whole thing out, the square root of x squared. No derivative of it, just square it. Leave it alone and square it. So I don't know about you, but that doesn't look like the answer we got a minute ago yet. There's like a bunch of algebra between us in there, but let's see if we can figure this out. So let's see, if I distribute x to the 1/2 into this mess right here, x to the 1/2 times that, that'd be 3, and you add exponents, so that'd be 4/2 plus 1/2, which is 5/2. And then 4x times x to the 1/2 would be x to the 3/2, because it'd be x to the 1 plus x to the 1/2. 1 plus 1/2 is 3/2. And so, okay, that's great. And then let's see what happens to this minus sign over here. Well, that's a mess. Let's see, when I distribute this over, I get 1/2. So, okay, that's cool. So there's a minus sign. And then it's 1/2, and then it's x to the 3rd times x to the negative 1/2. Again, you add those exponents. So that'd be 6/2 minus 1/2, which would be 5/2. And then notice this minus sign distributes also. So this is going to be a minus sign too. And then it's 1/2 times 2, which is conveniently just 1. And then x squared times x to the negative 1/2. That'd be x to the 4/2 minus 1/2. That'd be x to the 3/2. And then on the bottom, I would square the square root of x and I'd get x. Again, pretty easy to make dumb math mistakes here. Kind of need to check my work over. And obviously your brain may be hurting because your algebra skills aren't allowing you to multiply that out easily, but it's like adding exponents and all that, and you're doing fractions in your head. And so then I look at this and I think, okay, cool. I see that these are like terms. 3 of them minus 1/2 of them, that would be 2.5, or 5/2 of them. Notice the description doesn't change. 3 apples minus 1/2 an apple is 2.5 apples. The x to the 5/2 doesn't change. And then I have a second set of like terms there, which is, hey, look, some number of x to the 3/2 minus another number of them. Oh, really nice, whole numbers. 4 of them minus 1 of them would be 3 of them. All over the top of x. So I'm wondering, is that our answer? I'm going to copy it down there and stare at it. I got to shut up here. I see the time, but is that our answer? Did it work?
Yeah, it worked.
Yeah, notice in a sense on the top, we're still not done simplifying. So because this is x to the 1st, and because of distributive law, both of these terms are divided by it. And so you're actually subtracting exponents. So 5/2 minus 2/2 would be 3/2. And 3/2 minus 2/2 would be 1/2. And so it worked. And so like, it's kind of a bummer that the quotient rule is so stinking complicated, but it's like it works, and you don't have a choice. Nobody's doing this to you. It's just the way reality works. I wish I could fly. Just can't. Don't have enough feathers on my wings. So you know enough right now to, do the entire assignment that's 3.4 tonight. I'm going to save a little bit of time. It's sort of the first half of tomorrow. We basically have 3 days to do 3.4 and 3.5. So we'll kind of maybe play with this a little bit more because we haven't practiced this enough. I just showed you the quotient rule and the product rule, and we did just a couple of quick examples. So we'll probably start off tomorrow just playing around with a few examples. But you know what you need to know right now. It wouldn't surprise me if you could get through the lion's share of 3.4's assignment right now. But you should also notice there's a lot of algebra coming up here. You're probably not doing the algebra near as quickly as I am. You're probably not near as good at these rules. Please, I beg you, start tomorrow with some of these problems. Like, why do you do this? Why do you add exponents when you multiply, and why do you subtract them when they're divided? Like, make sure you're getting to the bottom of that stuff. And then the more you can do basic math in your head, like when I'm going 3 plus a half, the fact that in my head I can say 3 is 6 halves plus 1 half is 7 halves, the fact that I can do that in my head keeps me from getting lost. I mean, this is quite a recipe, and it's so easy to get lost in it. If you can't do basic math in your head, that stuff is worth practicing. Then you're going to miss these kinds of things. And then, of course, as I mentioned on the test, it's a tall order for anybody to get through this without making some kind of a dumb mistake, even if they do know what they're doing. So, write clearly, but you know what you need to know now. So you have your third rule: power rule, product rule, quotient rule. And ready to kick some butt. All right, get out of here. Stay after as usual if you have questions about the project or questions about what we talked about today.
Thank you.
You are welcome. See you tomorrow. You good, Logan? See you later.